packed my bags last night, pre-flight.
Hello once again, AP Calculus students. Mr. Record here from Avon High School. We're going to talk a little bit more about related rates. And in this particular problem, we're going to talk about rotating cameras, space shuttles, and changes of distances and angles and anything else that we can throw in there. So if we read the problem, it says we've got a camera mounted 3,000 feet from the space shuttle launching pad. The camera needs to pivot as the shuttle is launched, and it needs to keep the shuttle in focus. If the shuttle is rising vertically at 800 feet per second when it is 4,000 feet high, how fast is the camera to shuttle distance changing? Now, you notice that you've got a completely blank canvas. Maybe in some of the other problems that we've done as a class or some of the other videos that I have made, you've noticed that some of the problems are already scaffolded where they ask you to draw a picture and find some other information. None of that is here, so we're kind of on our own. But with that in mind, problems such as this that seem to have a lot going on with them very likely will already have a picture drawn. All right. So I wouldn't worry so much about you guys having issues with exactly what's happening in the situation. So I'm going to draw a space shuttle platform. That's what they look like, apparently. And we have a camera that's on the ground that I'm going to put over here to the left. And cameras typically go on the ground, I guess. And then we have the space shuttle that eventually might be like launched up in the air. All right, so here's our space shuttle. And we know that this camera is going to be tracking the shuttle, so I'll kind of have it drawn to say like the tip. And we can see that we can complete the picture of a fairly familiar shape. All right. So the thing that we want to do now is start addressing what kinds of values that we have that make up the features of this triangle. For example, down below, the distance that the camera is from the space shuttle base. We ask ourselves, is that a variable or a constant? And the problem reads the camera is mounted 3,000 feet from. So I got a feeling that that's going to be a constant, right? The camera's not going to move. The space shuttle launching pad definitely is not going to move. So we have it locked in. And then we look over here maybe at this vertical side. That would be the side that the shuttle would be from the ground. And is that going to be a variable or a constant? Let's hope it's a variable, right? It wouldn't be very interesting otherwise. I can prove that it's a variable. Want to see? Yep. Nope, not you. There. USA. We know that y's got to be a variable. And then the actual distance that the camera is from the tip of the shuttle is going to be a variable as well. We're going to call it z. You can call these virtually anything that you want, though. But as that shuttle gets higher and higher, the distance from the camera is going to become greater as well, most likely. So we've got the inner workings of our picture. If we have to go back to the picture and do more with it, we can certainly do that when the time comes, when it calls for it. So now what we're going to do is start putting down what I like to call the very vital components of the setup. That would be the given, the find, and the equation. Now the given is typically going to be some rate that the problem mentions. So we've kind of got the 3,000 already introduced into the problem. If we keep reading, we see this sentence here. If the shuttle is rising vertically at a rate of 800 feet per second. Well, that seems to kind of indicate the change of this value y. So we can use calculus notation, derivative notation specifically, and say dy over dt, and that would be 800. And it would be positive because we don't want the shuttle kind of burrowing into the ground. That would be bad. It's going to be rising from the surface of the Earth, thus a positive distance change. All right, now we take a look at the find. The find is usually associated with the question in the problem. And the question asks, How fast is the camera to shuttle distance changing? So we might find ourselves gravitating back to the picture. I think this is one of the better illustrations of a problem where the picture can be looked at many, many times throughout its solution. And we see that this is probably that distance, right, from the camera to the shuttle. So we want to find out how he is changing. So that would be our dz dt. And specifically, you're going to want to find that when the shuttle is 4,000 feet off the ground. A lot of times, a student may not remember to put that when y equal 4,000 next to that, and it's really not a terrible thing. You will probably discover that you're going to use 4,000 for y eventually. And then we need an equation. Sometimes the equation is rather easy to see. Sometimes it's a little bit more complicated. Usually in a problem where you have a right triangle and nothing but sides being mentioned and referred to, you're looking at the Pythagorean theorem. And that's what we're going to have here. 3,000 squared plus y squared equal to z squared. For my students currently in my class, very similar to a problem we did yesterday. And very similar to a lot of the problems that you had assigned last night. You were doing a lot of them there in bunches that dealt with the Pythagorean theorem. So the next thing that we are going to do is take the derivative of this. Don't bother yourself with squaring 3,000. It's a waste of time because his derivative is 0. And don't want an equals just yet. How about a plus? Now the derivative of y squared would be 2y dy dt. And we would set that equal to 2z dz dt. Now, anytime that you use the Pythagorean theorem and you take its derivative implicitly, you're typically going to have a bunch of 2's that you could actually just kind of cancel away because you could divide all the terms in the equation by 2 and they're not going to really amount to anything. Makes the problem a little cleaner. And then we're going to start plugging in stuff we know. Right away it asks for a y. Well, we know y. Isn't it nice to have written this there? Because you can go right to it and fill it in. Then it wants to know what dy dt is. Well, dy dt is 800. Fill it in. And then that's equivalent to, and we come to z, and we get a little disappointed because it's like, z, what the heck, z? We don't know z, but recall you've got a very specific situation on your hands. This space shuttle has climbed to a certain altitude where this is now 4,000. We know that the camera is still 3,000 from the launching pad, so if we use the Pythagorean theorem, or better yet, a nice 3, 4, 5 ratio right triangle, it will force that z side to be 5,000 at that instance. Okay? It's really important that we all understand. It might be tempting to plug in that 5,000 for that z very early, but you're not allowed to do that because z is going to change until the derivative is taken. Remember, when the derivative is taken, I tell my class that's like the power to freeze time. Once that derivative is taken, shuttle stops, it's 4,000 feet above the ground, and then we can start addressing, you know, what the other values are going to be at that split moment. Okay? So we're going to use 5,000 for z, and the dz dt is going to stay just that, dz dt. That's what we're trying to find. So we multiply 4,800 and we get like a really big number. How about 3,200,000, I think? And that's equivalent to 5,000 dz dt. So far we've done well in not having to use a calculator. I don't think we're going to really need one. Because you can divide by 5,000. I know it's a little scary, but in finding dz dt, the first thing that I would suggest is to cancel out 3 zeros from the top and 3 zeros from the bottom. And you would get 3,200 over 5. And if you do a little investigative work here, I think 5 goes into 3,200 like 640 times. It's not difficult to see that. If you had to do that by hand, I wouldn't worry. And since this is the rate of change of a distance, we would want just a linear measure of this unit, which would be feet, and the time is still seconds. And that's how quickly the shuttle and the camera are sort of, well, moving away from each other. Of course, only the shuttle is the thing that's moving, but all right. Now we're going to move to part B, which it utilizes the same problem, which is great because we're not going to have to like reset a bunch of stuff. But I'm just going to ask a slightly different question. So we're considering the same problem, but this time I want to know how fast is the angle of elevation of the camera changing at that moment when the shuttle is 4,000 feet high. So rather than kind of draw another elaborate picture with my space shuttles flying all throughout the sky, which I know you loved to see, what we're going to do instead is just draw the basics here. We're going to draw that 3,000 feet long distance at the bottom. The shuttle's still moving, so our distances y and z are maintained. But now the problem wants to know what is going to be the angle of elevation. So it seems like there's another thing in the picture that needs to be labeled, and that would be some kind of angle, right? And the angle of elevation, you've got three angles, and it may possibly be confusing as to which one is the one that we're dealing with, but it's the one that's going to be focused on where the camera is. It's how fast this angle is changing. So we need to give it a name. Typically in mathematics, we use Greek letters to name angles. It's not like it would be the end of the world if you used something different, but I would stick to Greek letters, and the most famous Greek letter for an angle is theta. I almost use that exclusively. But you could pretty much use any Greek letter out there. I would avoid pi. All right? So now that we have this, we probably ought to revisit our statements now because they may alter a little bit. Given, find, and equation. Well, because there's no other rate that has been given to us in Part B, we are going to revert back to Part A. And when Part A said that the shuttle is rising vertically at 800 feet per second, that is going to apply down here as well. And that would not be dz, but that would be dy dt. Now, our find is certainly going to be different. We want to know the rate of change of this angle, so we are going to use d theta dt. That's the first time for us as a class right now. And for our equation, I don't think the Pythagorean theorem is going to come to our rescue now. Because we're dealing with an angle change, we're not going to be dealing with algebra anymore. We're not going to be dealing with geometry. What class are we going to now deal with in the problem? Trigonometry, right? So the trigonometry that we're going to use is going to focus on one of the 6 different trig ratios. And you really, in this particular problem, you could use any one of the 6 only because there was a part A that we answered already. But if this was a standalone part, I really want you to maybe not use all or any of the 6. I want you to use a very specific one. And just think logically about this picture. Of these 3 numbers, do you feel like it would be very advantageous to use the 3,000, to use a constant? Right? Constants are very easy to work with. So I think you ought to use a trig ratio that somehow incorporates the adjacent side to this angle. So now you just got to pair it up with either z or y. Are you going to use opposite and adjacent? Or hypotenuse with adjacent? Well, which value do we know more about? Z or y? Look at your given and find. That's probably all you need. You already see that dy dt has been given to you, and although I didn't write it, this d theta dt that we're trying to find, we're going to try to find it exactly when that shuttle is 4,000 feet above the ground. So we have more information about y. Now, like I said, from part A, you had information about z, but pretend that we didn't. And I think it will be very clear that we want to utilize these 2 values, opposite and adjacent, which would be the tangent. So that's our equation. The tangent of theta is equivalent to opposite over adjacent. You don't always use tangent in some of these problems, I've seen a few where sine and cosine may come into the picture. It seems like, though, in the vast array of textbooks that I've looked at, tangent does seem to be the most popular. All right. And I think it's because vertical and horizontal measurements in real life are a lot easier to focus in on than this diagonal measure. All right, so now we're going to have to take the derivative of this equation. So the derivative of tangent of theta with respect to t is secant squared of theta. There is no substitute for knowing your trig derivatives very well, backwards and forwards. We're going to tack on a d theta dt there. And we're going to set that equal to the derivative of y over 3,000, which is 1 over 3,000 dy dt. dy dt. Okay? Now we just start plugging in our values. And we also want to be sort of cognizant of the fact that it's the d theta dt that we're trying to solve for. So I'm going to kind of box that in to reinforce that that's my variable. So when you come across the secant squared of theta, it's really easy to kind of be intimidated and think, oh my gosh, what am I going to have to do with that? Well, again, just go back to your picture. Right now we have sort of a freezed frame picture. We've got this space shuttle that's way up here, right? 4,000 feet high. 3,000 is still our base length. We remembered from the previous part that the hypotenuse is 5,000. Well, if we know all three sides of our right triangle, I think we could find virtually any trig ratio that we wanted. So if we wanted the secant squared of this angle, you've got to think about the fact that secant of theta is the reciprocal of cosine. So we would just go about finding the cosine and then flipping that answer upside down, and then I believe that we're going to have to square it. So the cosine of angle theta would be, normally it would be the adjacent, or I'm sorry, yeah, the adjacent over hypotenuse, right? 3,000 over 5,000, that's the cosine. But since we're going to reciprocate it, we're going to call it 5,000 over 3,000. And yep, that will be squared. The d theta dt will stay as he is, and the dy dt is our 800 that we have here in our given. Now, I know that 5,000 over 3,000 squared is a bit scary, but you could make this a lot simpler by canceling a ton of zeros and then squaring what's left and getting 25 ninths, because it's all going to reduce to that anyway, multiplied by d theta dt. And on the right side, I want to say that the 800 over 3,000 would reduce to, well, 8 over 30, which further reduces to 4 over 15. Now all that needs to be done is we divide both sides by 25 ninths, or multiply by 9/25ths. And you can do a little reducing with the 9 and the 15 if you'd like. And 12 over 125 seems to be the results. 12 over 125 does not reduce anymore. It may be hard to kind of relate to that. But we do need to give the problem a label. And that's usually the last little trick to these kinds of rate of change of angle problems. And there really are two different labels that you can attach to an angle. One's wrong and one's right. In this case, we must use radians, not degrees. And our time element, I believe, was it seconds? Yeah. So radians per second. We could get into a long spiel about why radians and not degrees. I think the short of it is that degrees innately have a symbol attached to it, the little degree symbol, where a radian does not have that symbol. And because of that, a radian is much more freer to be manipulated and multiplied and worked with in a mathematical capacity than a degree is. Now, if you're kind of wondering, well, what does this really mean? I suppose that we could open the TI Inspire software, which will take just a moment here. Yep, I did not come prepared. And we could convert this 12 over 125 radians into degrees fairly quickly. Um, and let's see, if we do that, we'll just go to a scratch pad here. How's that? And we can just type in 12 over 125, real simple. And then the formula for converting to degrees is multiplying by, what is it, 180? Not 80, not there. Not there at all. 180 on top over pi. And I'm going to throw a decimal point so it gives me a nice decimal answer. And I get about 5.5. 5.5 degrees per second, which doesn't seem like a very big degree measure, but, you know, in just a few seconds, that's going to open itself up pretty wide. All right, so that would be our answer. So anyhow, there is your space shuttle problem with both finding the rate of change of the hypotenuse and finding the rate of change of the angle measure. Anyway, I hope this helps out, and good luck to you.